Supervised learning techniques, a deep dive into predictive modeling. Welcome to our channel, your go-to destination for comprehensive and accessible deep dives into the world of artificial intelligence and machine learning. Whether you're a student, a data science enthusiast, or a seasoned professional looking to refresh your understanding, you've landed in the right place. In today's video, we're embarking on an exciting journey through the realm of supervised learning techniques. This isn't just a crash course. It's an in-depth exploration designed to help you grasp both the theoretical foundations and practical applications of some of the most essential tools in the machine learning toolkit. We'll walk through everything from linear and logistic regression to decision trees, support vector machines, and finally, model evaluation and hyperparameter tuning. So sit back, grab a notebook or open your favorite IDE, and let's get started. Introduction to the topic. Supervised learning is one of the most fundamental categories of machine learning. Unlike unsupervised learning, which works on unlabeled data, supervised learning requires a dataset that includes input-output pairs. The model learns by comparing its predictions with actual outcomes and adjusts accordingly. This technique is the backbone of numerous real-world applications, from email spam detection and fraud identification to customer churn prediction and personalized recommendations. Mastering supervised learning techniques not only lays the groundwork for more complex methods like deep learning, but also enables you to build high-performing predictive models that solve practical business and scientific problems. In this video, we will explore 6 major components of supervised learning: linear regression and its applications, logistic regression for classification problems, decision trees and random forests for hierarchical and ensemble learning, support vector machines for optimal margin classification, and finally, how to evaluate and fine-tune models effectively. Main content. Section 1. Linear regression and applications. Linear regression is often the first algorithm introduced in a machine learning curriculum, and for good reason. It is intuitive, interpretable, and surprisingly powerful for predicting continuous outcomes. The core idea is to establish a linear relationship between independent variables, features, and a dependent variable, target. Let's consider a scenario where a retail company wants to predict its monthly sales based on advertising expenditures across TV, radio, and online platforms. Using multivariate linear regression, the company can understand how each advertising channel contributes to sales. The coefficients in the regression equation indicate the magnitude and direction of impact of each feature. The model can not only predict sales for future months, but also help optimize the ad budget for maximum return on investment. Another practical example is in healthcare, where linear regression can be used to predict a patient's recovery time based on age, pre-existing conditions, and treatment methods. By analyzing historical patient data, hospitals can better estimate recovery durations and allocate resources more efficiently. Despite its simplicity, linear regression assumes a linear relationship, homoscedasticity, and independence of errors, assumptions that must be validated to avoid misleading conclusions. Section 2. Logistic regression for classification. While linear regression deals with continuous outcomes, logistic regression is employed for categorical outcomes, particularly binary classification. The technique uses the logistic, sigmoid, function to map predicted values between 0 and 1, effectively producing probabilities. Take, for example, a bank trying to predict whether a customer will default on a loan. Based on features like income, credit score, loan amount, and employment status, logistic regression can assign a probability of default. Customers with probabilities above a certain threshold are flagged for further scrutiny. Another common application is in email spam detection. Logistic regression can be trained on labeled datasets where emails are marked as spam or not spam, based on features such as email content, sender information, and subject lines. Despite its name, logistic regression is a classification algorithm and does not rely on a linear relationship between the input features and the output. However, it does assume that the log odds of the outcome is a linear combination of the input variables, which is an important distinction to remember. Section 3. Decision trees and random forests. Decision trees are a popular choice for both classification and regression problems. They work by recursively splitting the data based on feature values that result in the greatest information gain or Gini reduction. The model is visually interpretable and aligns well with human decision-making processes. For example, consider a telecom company trying to predict customer churn. A decision tree might split first on monthly bill amount, then on contract length, followed by usage statistics. At each leaf node, the tree outputs a classification, likely to churn or not. However, decision trees are prone to overfitting, especially if the tree is deep. This is where random forests come into play. A random forest is an ensemble of decision trees trained on different subsets of data and features. It reduces variance and improves generalization by averaging multiple trees' predictions. Imagine an insurance firm using a random forest to predict the likelihood of claim fraud. Individual trees may overfit to specific patterns, but the ensemble smooths out these idiosyncrasies, resulting in a more robust model. Section 4. Support vector machines, SVM. Support vector machines are powerful classifiers that aim to find the optimal hyperplane that separates classes with the maximum margin. SVMs are particularly effective in high-dimensional spaces and are robust against overfitting, especially when the number of features exceeds the number of samples. Consider a medical diagnostic tool that classifies tumors as benign or malignant based on features like size, shape, and texture. An SVM can draw a hyperplane that maximizes the distance between the two classes, reducing misclassification risk. SVMs also support kernel functions, enabling them to handle non-linear relationships. A radial basis function, RBF, kernel, for instance, can project data into a higher dimensional space where a linear separator becomes feasible. Another example involves handwriting recognition. Each handwritten digit can be represented by pixel intensities. SVMs can learn to distinguish between digits with high accuracy, even when written in varying styles. Section 5. Model evaluation and tuning. Building a model is only half the battle. Evaluating and fine-tuning it is crucial for achieving optimal performance. Common evaluation metrics for regression include mean squared error, MSE, root mean squared error, RMSE, and R-squared. For classification, metrics such as accuracy, precision, recall, F1 score, and ROCAUC are widely used. Let's revisit our email spam classifier. Suppose it achieves 95% accuracy, but 90% of emails are non-spam. This could indicate poor performance in identifying actual spam emails. Precision and recall give a more nuanced picture, particularly in imbalanced datasets. Model tuning involves adjusting hyperparameters, such as the depth of a tree, regularization strength in logistic regression, or the kernel type in SVMs, to find the best performing configuration. Techniques like grid search and random search, often combined with cross-validation, help automate this process. Using k-fold cross-validation, we split the data into k subsets and test the model k times, each time using a different subset as the test set. This helps mitigate overfitting and provides a more reliable estimate of model performance. Tips, best practices, understand the data. Always start with exploratory data analysis. Visualize distributions, identify missing values, and detect outliers. Quality data is the foundation of any good model. Feature engineering matters. Deriving meaningful features often has a bigger impact than choosing a complex model. Normalize numerical features and encode categorical variables appropriately. Avoid overfitting. Use regularization techniques like L1 or L2, prune trees, and monitor performance on validation sets. A high accuracy on training data alone is not a good sign. Start simple. Begin with interpretable models like linear or logistic regression before moving to more complex algorithms. These simpler models often serve as strong baselines. Document and reproduce. Keep track of model versions, parameters, and data splits. Reproducibility is key in both academic and business settings. Keep the business objective in focus. Never lose sight of the end goal. Model accuracy is important, but actionable insights and decision support are what truly matter. Congratulations! You've just completed a comprehensive journey through some of the most widely used supervised learning techniques in machine learning. We've covered everything from the basic intuition behind linear regression to the complexities of support vector machines and the fine-tuning required to bring models into production-ready shape. Whether you're prepping for a data science interview, working on your next big project, or just expanding your knowledge, these concepts form a solid foundation that will serve you well. If you found this deep dive helpful, don't forget to hit that like button, subscribe to our channel, and click the bell icon to get notified about our upcoming videos on deep learning, reinforcement learning, and real-world AI applications. Have questions or topic suggestions? Drop them in the comments below. Until next time, keep learning and stay curious.